Forces are fascinating, aren't they? They govern everything around us, from the way we walk to the way objects interact with one another. Today, let's delve into the concepts of forces and elasticity, exploring how we can stretch, compress, or bend materials, and how these actions transfer energy in remarkable ways. When we apply a force to an object, we create a change in its shape or size, and this change is where elasticity comes into play. Imagine a rubber band. When you pull on it, you're applying a force that stretches it. This stretching occurs because the molecules within the rubber band are being pulled apart, but they're not permanently displaced. Instead, they have the ability to return to their original shape when the force is removed. This property is known as elasticity. Now let's talk about what happens when we stretch something. When we apply a force, we do work on the material transferring energy into it. This energy is stored as potential energy in the form of elastic potential energy. The more we stretch the rubber band, the more energy it stores. When we release it, that stored energy converts back into kinetic energy, causing the rubber band to snap back to its original shape and propel forward. This principle is not just limited to rubber bands. It applies to various materials, including springs and even biological tissues in our bodies. The relationship between force and extension is governed by Hooke's law, which states that the extension of an elastic object is directly proportional to the force applied to it, as long as the elastic limit is not exceeded. This means that if you double the force, you will double the extension. And if you triple the force, the extension triples as well. It's a beautiful linear relationship that allows us to predict how materials will behave under different forces. But what happens when we push this relationship to its limits? Every material has an elastic limit, a threshold beyond which it can no longer return to its original shape. If we apply a force greater than this limit, the material undergoes plastic deformation, meaning it will be permanently deformed. Take a paperclip, for example. If you bend it gently, it will return to its original shape. But if you bend it too far, it will not recover. This is because the force applied has exceeded the elastic limit, causing the internal structure of the material to change irreversibly. The fascinating aspect of this is how energy transfer is affected. When we exceed the elastic limit, the energy that was once stored as potential energy doesn't convert back into kinetic energy in the same way. Instead, some of that energy is dissipated as heat due to internal friction within the material. This is why when you stretch a rubber band too far, it can feel warm to the touch after being released. In summary, the interplay of forces and elasticity is a fundamental principle that governs the behavior of materials. When we stretch, compress, or bend an object, we transfer energy into it. And as long as we stay within the elastic limit, that energy can be stored and released efficiently. However, once we exceed that limit, the relationship breaks down, and we see a permanent change in the material, accompanied by a loss of energy in the form of heat. Understanding these concepts not only helps us appreciate the materials we interact with daily, but also informs the design of everything from simple toys to complex engineering structures. It's a reminder of the delicate balance between force and elasticity, and how, in the world of physics, pushing boundaries can lead to unexpected outcomes.